Good morning. Welcome back to docket number 2105, 15 REO3. HERA's investigation into the establishment of integrated distribution system planning within a performance-based regulation framework. My name is Chairman Marissa Gillette. I'm joined virtually today by my colleagues, Vice Chairman Jack Bukowski and Commissioner Michael Perrin. We are here today for the third technical meeting in this matter. And we have an agenda in front of us today. We're going to receive a presentation from our colleagues at the United Illuminating Company first, followed by HERA staff questions. If we have time for stakeholder questions, we will take them. We'll then move into Eversource's presentation, followed by questions. We did carve out time today for stakeholders to make any comments that you have in reaction to the presentation, if you so choose. Otherwise, of course, welcome to do that in writing as well. We'll briefly cover next steps before closing. We did not carve out time for a lunch break today because we anticipate wrapping during the lunch hour. So hopefully everyone bears with us through that. Just a couple of quick reminders, housekeeping items. We are streaming on YouTube. We have a court reporter with us today. Please refrain from using the chat function as it is not part of the official record. We ask that you make sure you are identifiable by name and affiliation if you are going to participate in the conversation for purposes of the record. With that, we will invite our United Illuminating Company colleagues to the virtual floor. And just start with a question about whether you would like Ms. Looply to control the slide deck, or if you would like to, and after answering the question, the floor is yours. Good morning, gentlemen.
Good morning, Chair. Good morning, Commissioners. My name is Michael Pertell. I'm here presenting for United Illuminating. Also, my associate, Lucas Cruz, will be bringing up the tail end of the presentation, and if you wouldn't mind, I would prefer to share the screen. I think it goes much smoother. Without further ado, give me a second here. Let me know if you see the load forecast on the screen.
Not yet.
Oh. What are you seeing?
You. just
Lovely. Lovely. All right, let's try again. There. Okay, I got it. Better?
Yes.
Perfect. All right. Apologies. I'm more of a Teams user. So good morning, all. Thank you for this opportunity for us to present what we currently do with respect to the load forecast to support integrated system planning and the distribution planning of the UI system. I also want to talk about some points about what we're currently undertaking as far as development and improvement and revisions on the process, as the technology in this space is advancing very rapidly. So this slide was presented in technical conference number 2 by Lucas, and it's kind of like an overview of the integrated system planning model for the peak forecasting. UI starts with a corporate level, top down for the UI total distribution system. And what I've added to these little blocks is kind of like the source of the data for some of these particular steps in the process. UI's historical peak, we generally rely on our SCADA data. We also, since we're getting into analysis at the granular level, we incorporate our AMI data as well. And that's one of the developments I'll talk about later. For weather normalization, we use hourly weather, and we align it with the hour of the peak. And we test in our normalization. I say normalization, it's actually adjusting the weather to design conditions in this scenario, right, for peak. We test various aggregations of weather, whether it's over a multi-hour period or a multi-day period, to see if we get the best fit to reflect the weather response. When we build the forecasting model, it's an econometric model of the adjusted peaks. We have some underlying economic assumptions. We get that data from IHS Markit, which is one of the top 40 economic houses, if you will, that feed into Blue Chip. We get their data down to the county level. The software that we primarily use for both our normalization regression models and our econometric forecasting models is MetricsND. That's provided by Itron. This is specific to utilities, whether it's electric, gas, or water. MetricsND is used by about a third of the utilities within the US, as well as many of the independent system operators. We do our forecast, and then we have incremental out-of-model adjustments, pretty much for items that we cannot yet, and I say cannot yet because part of statistical modeling is you need a sample, and some of these disruptive technologies are in their infancy. So we want to build a couple of years of samples before we can get to the point where we can incorporate them in the model. So at this point, we make incremental adjustments for future load disruptors. And I say disruptors because some will increase the peak and some will decrease the peak. Our growth assumptions for a lot of these distributed energy resources, we adopt what the ISO New England puts out as far as their SELT report, and we scale them to UI's service territory. So I'm going to peel away the onion a little bit from what that first slide was showing. But let me set the stage here. This chart shows roughly 17 years of UI's actual summer peaks. The black dots represent the peak, and the two lines here represent what our adjusted peak would be if we had the design conditions, either 50-50, which is for our internal budgeting, or 90-10, which is for system planning, distribution planning. And a sniff test of this, the reasonableness would be 50-50 means this is a peak that we would expect to occur once every 2 years. Another way to say that is if we use the norm inverse function is the probability of occurrence of 10% or of 50% each summer. So looking back on the sample, that would mean if we expect it once every 2 years, roughly half the sample would be above that red line, half below, and that seems to pass that test. The bluer line is our design condition for distribution planning. That's a weather condition that we would expect to occur once every 10 years. Again, stated another way is the probability of occurrence is 10% each summer. So we see that we've had one actual peak in the last 16, 17 years that has hit that weather condition. So that again passes that smell test, if you will. So how do we do these type of adjustments? Our peak forecast is really a two-step process. Our first step is to analyze the most recent summer, the daily peaks. And then we want to adjust that, estimate the weather response and adjust that to the design conditions. And since we're talking distribution planning, our design conditions is a 1 in 2 or a 90-10. I'm sorry, 1 in 10 probability occurrence of 10%. So we calculate that on the table on the right here. We've got the THI. Actually, let me explain what the THI is. THI is a temperature humidity index. This is the general formula over here on the left. This is kind of a standard THI. We've tested different variations of the THI. And it's a measure of the level of discomfort in the summer. It's a combination of TDB, which is temperature dry bulb, and temperature wet bulb. Dry bulb is just the temperature of the air measured by a thermometer, protected from radiation or moisture. Wet bulb, that's the temperature at which a person can reasonably be cooled by the evaporation of moisture with constant barometric pressure. So we combine that type of temperature and humidity. Wet bulb is captured in the wet bulb. And we align that weather condition with what occurred, when the peak occurred in history. So in this table, we see we've got 10 years of peak inducing summer weather temps. And to calculate the design condition, we use the norm inverse function. Probability of occurrence at 10% here is 85.3. So we're going to take the actual temperature that occurred on the peak day of the most recent summer. We're going to use this regression model to calculate the weather response, essentially the megawatts per THI. We're going to isolate weekends and holiday impacts with dummy variables. And we're going to use that adjustment to calculate the difference between the actual THI and the design THI times whatever the weather response. So we do this each year at the end of each summer. We're currently now building to do a similar process for the winter, given the increased proliferation of air source heat pumps and electric vehicles. Particularly home charging has a higher impact on residential winter peaks as opposed to residential summer peaks. So we want to capture those in our models to show when and if certain substations will convert from a summer peaking to a winter peaking, right? Any questions on this before I move on to the next? Okay. This is standard practice across the industry. The second step would be taking those adjusted actual peak, and again, I want to refrain from saying weather norm because that would assume normal weather. We're assuming design weather. We take that adjusted actual peak for each year in our sample, and we regress that on an underlying economic variable, which would capture the organic growth, as well as the DER, distributed energy resource output at the time of the peak. Here's our little table down on the right that shows each of our distributed energy resources. And then we've aligned their output in some cases, like the PV rooftop that's behind the meter, that we don't really have a full production generation. We estimate hourly loads. We simulate what the output based on nameplate rating using NREL's model. And we've aligned with what the output would be at the peak or was at the peak. So we're building a time series essentially of DER output at the peak so we can incorporate that into the model and hopefully estimate a response. Underlying economic variable, we retest that every summer. This is the annual process. We refresh it every year. We use the various factors from IHS Markit, whether it's a combination of employment or GDP manufacturing, or we also test our volumetric, our energy sales, which is a buildup of each of the different customer classes, residential, commercial, industrial, and then we have the assumed CLM impacts within that. And that would implicitly have the underlying growth assumptions provided by IHS Markit. So as with any type of modeling, the fit is only as good as the data. So this is why we retest every year when we refresh. After we have that baseline forecast, we then make our incremental out-of-model adjustments for future growth of various DER, electric vehicle penetration, air source heat pump adoption, and these are based on the growth rates from the ISO CELT. The ISO CELT has growth rates for states, and then we scale that to UI, which is essentially the same because we're applying those growth rates to what's currently connected in the field. We're not incrementally growing the DER as an input to the model. We're making an incremental out-of-model adjustment. So we're holding the most recent year constant. So that way we have two different scenarios that we can run. We can say, if there were no further incremental DER, this is what our peak forecast would be. If we have an out-of-model adjustment for the assumed growth rates that are contained in the ISO CELT, this is what the adoption would be and what their impacts would be at peak. The CELT forecast incorporates assumptions with SCEF, LREC, CREC, NRES. UI provides that to DEEP, and then DEEP additionally provides that to ISO New England. We actually have a meeting tomorrow with the ISO New England Load Forecast Committee to go over the assumptions that are going to be used in this current year's CELT. And then this forecast feeds into a report that we present every year. We submit to the Connecticut Siting Council. And as the little box indicates, our time horizon for this process, we do a 10-year peak forecast. Obviously, if there's one-off studies, that horizon would change, but our baseline every year when we do the refresh is a 10-year forecast. So now we have a corporate level UI peak forecast. System planning needs it at a more granular level. So how do we get there? The corporate level is disaggregated across the 28 UI distribution substations. And several years ago, before integrated system planning and the granular availability of data, we did what would a uniform distribution, right? Analogous to a creamy peanut butter spread, right? If the corporate growth rate is this, we're going to assume that growth rate across all the substations. Where we're at now is we have more granular data. So we know where the pockets of adoption of, say, electric vehicle home chargers, rooftop PV, air source heat pumps. So we have what I would more describe as a chunky peanut butter spread, right? So we're identifying where the pockets are. That's of concern at the granular level for our system distribution engineers. And we're still using the ISO assumed growth rates for those particular disruptors. So we're currently working on processes. That's our next step, is to get to the point where we can do localized adoption modeling, whether it's a VASTA Fusion model. We've built some samples in Excel to do that. But in order to calculate those appropriately, you need enough history in the sample, right? Where on the S curve do you have those points of inflection? Those are determined by the data. The other way we can do that is there's some industry assumptions for states that have a little bit further along the line of EV adoption or air source heat pump adoption. But that's where we want to get to in our next steps. As I mentioned earlier, we are also doing this whole process. We're building a parallel process for the winter months. PV is a little bit more decreased in the winter months, but EV home charging has roughly double the impact on the residential winter peak as it does on the summer. And that makes sense because 25 years ago or so, when we had more penetration of electric heat and certain areas were winter peaking, we peak at 7 or 8 p.m. Folks get home from work, they start cooking, kids are turning on the computer or the TV or what have you. And that's also now when someone gets home and plugs in their EV for home charging. Versus the summer, when the peak is typically in the early afternoon, and with PV, it's been pushed later and later in the afternoon. You don't have a lot of that residential home charging. So these are the type of dynamics that we're looking to model, is as EV or heat pump penetration increases on a circuit or a substation, can we model that impact on the AMI load, to the 24-hour load shape 10 years out? That would better inform maybe potential non-WAR solutions, or system planning who wants to prioritize the capital improvement dollars to make sure our infrastructure is still providing safe and reliable service. So I'm going to pause there before handing it over to my colleague, Lucas, and see if there's any questions on that statistical modeling part before we get more into the electrical engineering part.
Thank you. I think we might hold our questions until the end, but let me check quickly with my staff if they have any questions I want to ask now.
Thanks, Chair Gillette. I'm good to hold questions till the end.
Okay.
All right. Thank you, Mr.
Hey, Mike, I believe this is not the next slide of our presentation. I have the bullet points before the map.
Oh, please. Let's see. Did I open the wrong? Oh, here we go.
Oh, yeah, it's yeah, the order has changed, but no problem. So good morning, everyone. Thanks for the opportunity to present in this technical meeting today. My name is Lucas Cruz. I'm the manager of the distribution planning team in UI, and I am presenting on behalf of our UI's planning group. Moving to system planning scenarios. Here we develop substation planning scenarios in an annual basis. So every year we receive the corporate level forecast that is developed by my colleague Mike. And then we use this system level forecast to develop our system planning scenarios. So we start working with the 10-year non-coincident peak forecast, which is based on the 90-10 weather scenario that Mike explained. And this serves as the bedrock for the substation planning. This forecast not only anticipates the future loads based on extreme weather conditions, but also serves as the basis for sizing assets properly to meet the projected demand. In our pursuit of reliability, contingency planning is also considered. We plan for emergencies by assuming that the largest DG at each substation is offline during peak load. And with this approach, we basically unmask the loads that are basically hidden by the DG output. As we reconstitute the output as the DG output as load, making sure that we don't rely on a single generation source, which is not controlled by the EDC. Also in the interconnection space, we conduct minimum load analysis to account for potential demand fluctuations and making sure that we mitigate any adverse impacts of DGs in low load periods. In terms of the development of scenarios, we develop a 5-year load project scenario, which is the basis for building capital plans for rate cases, for example. We also develop a 10-year project scenario, which serves as our guide for initiating mitigation actions. And these also help us to shape the long-term outlook of our company. With the scenarios developed, we identify the specific year that each need is expected to occur, and then we start the development of the solutions or the projects. We prioritize solutions in the distribution system level, which usually have lower costs and are more efficient. We seek, for example, for circuits reconfiguration, for load transfer among neighboring circuits and neighboring substations. We also seek for creation of new circuit ties to increase the number of alternative solutions. Then the grid upgrades, such as substation capacity increase, new distribution feeders, new substations are explored only when the solutions within the distribution system are not feasible. And in conclusion, our load forecast analysis is not just a projection per substation. It's a proactive strategy to ensure that our distribution system is prepared for extreme temperatures and also emergency situation as losing the largest DG output during the peak load. Can you move to, I think it's the previous slide, Mike. Yes. So based on the 5-year horizon, we developed this substation planning scenario, which is based on the trigger year 2026. And as I said before, we update these scenarios in an annual basis to make sure that we are accounting for any change on our forecasts and in our data. And this is the year, the 2026 for this map. This is the year which the capacity needs are expected to occur within the 5-year horizon. But as it is based on the 90-10 weather scenario, it doesn't mean that the expected capacity constraint will necessarily occur in 2026. but in truth, it means that there is a chance of materializing depending on the temperatures on that year. So our company needs to be prepared for this type of situations. And looking at the map, we have identified 2 priority substations in the 5-year horizon. One is the Ash Creek substation in Bridgeport, and the other is the Indian Wells substation in Derby. And both are exposed to exceeding the 90% thermal loading in 2026. And based on that, our planning team developed capacity projects, or AKA solutions, in order to mitigate that risk. Mike, can you move to the 10-year horizon map? Yes. Sorry, the previous one. I misstated. Yes, this one with the solutions. This map represents the scenario after the implementation of the mitigation solutions that I mentioned. This portfolio of solutions involves transferring loads from Ash Creek substation to neighboring substation as Hawthorne and Pequannock using the distribution system ties. Also, moving loads from Indian Well to Ansonia and Putatuck. And with these solutions, we are able to postpone the need for major upgrades on our grid, such as substation upgrades. Now, Mike, can you move to the, please, 10-year? Yeah. And lastly, based on the 10-year horizon, we developed this substation planning scenario, which is based on the trigger year 2030. Additional solutions are under development now in order to address the possible capacity constraints in North Haven, Ash Creek, and Indian Well. In this case, substation capacity upgrades might be explored if solutions within the distribution system are not feasible. And this is the end of UI's presentation. Thanks again for the opportunity to be presenting here.
Excellent. Thank you both. So I am going to invite questions from Kura's staff first, and we're going to turn to Mr. Kramer. If there are stakeholders with questions on the UI presentation, I'd invite you to get into the queue by using the raise hand function under the reactions tab at the bottom of the screen, and we will turn to back to you after Kura's staff questions. Mr. Kramer, please.
Thank you, Chairman Gillette, and thank you, Mr. Patel and Mr. Cruz, for the presentation. Very helpful to get a more detailed look at the load and DER forecasting process. I have a small handful of questions. My first one is around this idea of the top-down and the bottom-up planning process. And on the bottom-up approach, Mr. Patel, you described that, I think I understood that to be as something that is more in development at least at the corporate level forecasting, and the intent there is to do some localized modeling for distribution substations. And I wanted to understand the relationship between that planned bottom-up approach and what Mr. Cruz was describing with the 5-year scenario planning for substations. So could you help us understand the extent to which those two things are similar or different, right? Because the 5-year substation scenario planning, how is that different or similar to what you're working towards with distribution substation forecasting?
Okay, thanks for the question, Mr. Kramer. So we actually do have the bottom up for the summer months in place. We are developing for winter, right? We over the last 18 months, we've worked to get data from like Connecticut DMV, from the global website, there's this global stats of EV penetrations across each of the states, but the DMV of Connecticut seems to be a little bit more updated. We've mapped that to each of our circuits by address. So we have all of the EVs in place. Air source heat pumps, we've got that from our internal teams we've mapped where the heat pump adoption has occurred. And the assumption is there's a bigger impact in the winter. We'll assume heat pump adoption with the residual of central air conditioning is going to have an impact in the summer peak. Although if it's replacing portable window air conditioning, right, it's a net potentially decrease in load because it's more efficient. But we have that all mapped to distribution substation and their impact. And in the summer months, we currently have that to provide to Mr. Cruz's team. In the winter months, that's under development. And then further, we're looking to even go more granular with our own internal statistical forecasting. All of this constrained at the corporate level because that is designed to meet the policy goals, right? If we do unconstrained 28 different distribution level forecasts without taking into consideration what the policy goals are at the state level, then that might cause some angst, whether it's internally or externally. So this is what we're going to get to policy goals is our assumption. What Mr. Cruz needs is where we're going to get to it first, right? So where should we invest in our infrastructure? But we have that in place in the summer months, and that would feed into what Mr. Cruz was talking about with the substations. What he was showing there was a snapshot of the summer. This whole presentation is based on summer peaking, but we're working to develop the winter peaking in parallel.
Our objective in system planning, just to add to Mike's comment, is to determine the system impacts of that peak for each substation, and then develop the solutions that would mitigate the risk of those impacts.
Understood. Thank you for the clarification on the substation level planning and forecasting. That's helpful. And apologies if I missed it, but could you speak a little bit to how the top-down and bottom-up approaches are integrated? How do they sort of interface with one another in terms of the planning that takes place for the company?
So the top-down, the UI corporate level is used by multiple departments, right? Internal planning and budgeting and revenue type forecast, whatever. And integrated system planning, the design is Mr. Cruz's focus is on the granular level. So it's a way to marry the two and make sure that they are consistent. But I'm given that we now have more granular data, maybe 15, 20 years ago, system planning would only had a corporate growth assumption, and that's that creamy peanut butter spread, right? Let's assume that growth at all the substations. But now we're breaking out the granular bottom up, and ultimately that's going to be driving more informed investments, I think.
So if I understand that correctly, the top-down system peak forecast is developed at the corporate level, handed to Mr. Cruz's team as sort of here's the bigger picture for the system peak, and then with that they can look at how that would play out at each of the distribution substations and sort of plan for those 5-year scenarios that Mr. Cruz you were describing. Is that right?
Yeah, right.
Thank you. My next question is regarding, and this may just be a terminology piece. I recall from the presentation reference to the company's long-term outlook on slide 8. Is that the same thing as the 10-year forecast, or is that something different? And if it's different, could you please elaborate on what that is and its relationship to forecasting?
Yeah, sure. So the company's long-term outlook is basically our investment plan for the next 10 years, and which not the totality of our long-term outlook is included in rate cases. But we proactively start developing the capital plans for the next 10 years. So The 10-year load forecast is used to inform the long-term outlook of the company.
Understood. And that long-term outlook, is that updated annually as the forecast is, or more episodically as the company may be preparing for a rate case, for example?
It's updated, to my knowledge, it's updated every time that we identify a need. There is a committee which is it's in progress all years, and any need for investments are discussed there, and once approved, they are included to the long-term outlook.
Thank you. That's helpful.
I'm back. For some reason, I disconnected. All of you froze, and I thought I was the only one that was still connected, but apparently it was me. So I apologize. Thanks, Lucas.
No problem.
Okay. And then my last question, I believe, is regarding stakeholder or other party input in the forecasting process. So I think the points at which I saw that addressed in some way in the presentation and heard it was, I think, kind of considering the economic development loads, which would, as I understand them, are based on, new construction, new development projects, and those inputs coming to the company. Additionally, the clean energy or energy efficiency programs represented, either through the state or in the conservation load management plan, that get filtered up to ISO and then back down through the CELT. Are those the only stakeholder sort of input or feedback points in the process, or are there other points in the process that the company is gathering information from customers or others to inform its forecasting and planning?
So, for example, electric vehicles, right? There's a whole another docket and group of electric vehicle adoption stakeholders, and that's incorporated into our own internal EV team, and then they inform us of those type of assumptions. So I guess that's an indirect way that we're incorporating all of those assumptions into our forecast. Same with heat pumps, right? Those type of programs we get from our marketing, and we have some interaction so that whatever interface they have with rebates or what's going on in the space.
Understood. And then I guess relatedly, in terms of what comes back from ISO in the CELT report, has the company ever done just kind of a sense check or its own look at how the CLMP assumptions are represented, or the clean energy programs, to sort of do a check to see if you would agree that the way that the ISO feeds them back to you are what you would also expect to represent in terms of those out of model adjustments?
I want to say yes and no. I actually brought this up to John Black of the ISO in our last load forecast meeting in December, is how are we using the latest empirical data to inform our assumptions for all of these disruptive or out of model adjustments? And that's a topic that we're actually discussing tomorrow. So internally, we, in our annual refresh, when we're updating and getting the last 12 months of the heat pump adoption, and we compared that to what the assumptions were last year, it's a cyclical process, but we have not yet incorporated. It's just changing the slope to the policy goals, right? At this particular point.
So just on that last point, if I understand you correctly, it's not necessarily about where we'll end up, because that is more fixed, but instead it's how fast we get there, which would have implications for planning on a year-to-year basis.
Yes, and in the near term, where we're going to get there sooner rather than later, right?
Sure.
Because that's where we need to put our focus on infrastructure. Yeah.
Thank you. Chairman Gillette, that's all the questions that I have.
Good, then we do have time, so we will turn to stakeholder questions and see Mr. Walmsley. Sorry, he disappeared from me. And Attorney Talbert's legal, I can see your lips moving. I can't hear you. I hope it's not me.
I had double
Okay.
muted myself. Oh, Alex is back now. He's our
Okay.
consultant. He is back.
I had a hiccup as well. Sorry, folks. Alex Walmsley here from RMI, working with James and the team at the Office of Consumer Counsel. So my question is similar interest area to Mr. Kramer. I'm still trying to understand how the ISO New England CELTS forecast is disaggregated down geographically and topologically. Are you essentially saying you're using current data as a weighting? So you would weight where you think there will be more of an uptake of these out of model technologies and DERs? Or are you using a further data set? Like how you go from your creamy peanut butter to your lumpy peanut butter, like how you actually weight these different geographical areas?
Yeah, no, good question, Mr. Walmsley. Let me kind of further elucidate. We use the growth rate assumptions from the ISO CELT. We have our own mapping of what's in the field across the 28 substations. So if we have pockets of electric vehicles off substation 1 or 2, and we're assuming the ISO CELT growth rate of electric vehicles, that will show higher penetration in 5-10 years because it has a higher starting point. If we've got areas with a dozen electric vehicles, and we're applying the same, so we're not disaggregating the actual units or demand or associated with the CELT. We're taking the growth rate by assumption and adopting it or applying it to our starting point that we've already mapped out.
Thank you. That does clarify. Thank you for giving that clarity. Very quickly, if I may, I'm also just thinking about the terminology. Could you very briefly describe the difference between how you're terming a forecast relative to a scenario?
Well, I think multiple forecasts equal different scenarios, right? So if we have a forecast with 0 out of model adjustments, that would be scenario 1, baseline. If we have a forecast saying here we're going to meet the EV goals, that would be scenario 2. If we have our full assumptions of EV and heat pump goals, as well as CLM goals, that would be scenario 3. So it's really not type of a Monte Carlo type simulation scenarios. It's but for this or with this would be the different type of scenarios. But all of them are individual forecasts. If you're looking at that type of, depending on what your analysis pertains to, right? And system planning, they want the 90-10 weather scenario designed for the worst to make sure we can handle that type of load.
So to clarify, a scenario is an agglomeration of multiple parts of different forecasts. Is that correct?
Yes.
Okay, thank you. Thank you very much.
Great, thank you. Any other questions for our UI colleagues? Right. If not, Mr. Patel, Mr. Cruz, thank you for the presentation and thank you for answering our questions.
Thank you.
Thank you.
Very good. So we will move next into the Eversource presentation. I believe we have Mr. Freeman and Dr. Walker with us. So if you just let us know if you'd like to control the presentation or have Ms. Lucy do so.
Good morning. Yeah, if you could control the presentation, that would be great.
Great. Then as soon as it comes up, you all have the floor. Thank you for joining us this morning.
Okay.
Thank you.
Well, then I'll kick it off. Good morning, Chairman Gillette, commissioners. Thank you so much for giving us the opportunity to present today on our forecasting process and methodology. Let's go to the second slide right away. The way we've structured today's presentation is we've taken the specific requests that PURA had issued to the EDCs, and we've kind of built the entire presentation along those points. And we're going to try to answer each individual item as it was put forward with a slide or a couple of slides piece by piece. So the first thing we're going to start out is the inputs and assumptions. Next slide, please. So in the inputs and assumptions, there were 4 specific requests on information issued by PURA, starting off with a description of channels and data inputs that we're collecting for both our DER and load forecast. Next slide, please. On the channels for data. So there's a variety of data that's collected, and this is, I think, a slide that we've shown before, so we're just going to reuse this here. We do use historic weather data to make adjustments in the load and for solar corrections, looking at historic output of solar data. We have a variety of information for forecast data on the economy. We use customer data to do our socioeconomic forecasts, vehicle mobility data, census data. Parcel data flows into the solar forecast, climate projections for the long-term load forecasts. We also do step load tracking. That's our large-scale customers and new customer additions. You'll see this come up multiple times through the presentation. And then, of course, SCADA data that looks at our historic peaks at a station level. Thank you. The second point that was brought forward as a question was the relationship between policy documents and plans such as the Integrated Resource Plan and what we do in terms of our forecasts. I have a couple of slides to kind of dive into this a little bit more in detail. That's a bit more complicated. Next slide, please. So this is a slide, again, I apologize. We've shown this multiple times, but it really does show really nicely how the forecast is set up. We have our 10-year forecast. That's the 10-year forecast that triggers our capital projects. And then we have a long-term electric demand assessment that is done all the way out to 2050, but that is not used to authorize or trigger capital projects. Now, in both forecasts, the state policy objectives flow in as a top-down input into the forecast. So if certain goals are set within those state policy objectives, those inform the allocation of the load on our station. And that happens both in the long-term and in the 10-year forecast. Next slide, please. So here, and this is a slide again. I think we've shown this in the first technical session. I do want to quickly use this to just take a step back on this topic of how the policy impact goes into the forecasts. And the key item here is the grid needs assessment, which essentially is the forecast, is just one piece of this entire process. Right? So as we're building our forecast and we identify constraints in the 10-year time horizon that we've just seen on the previous slide, an entire machinery kicks into gear on our side to really identify what we can do to mitigate that need. And that includes anything from substation engineering. We need siting, permitting, our real estate group to look at properties if we do need to build a solution. Community relations gets engaged, system planning, transmission planning, protection and controls, and our distribution engineering group to use what's coming into these forecasts and really build out a solution that mitigates those needs. And I just wanted to, and as we're just talking about forecasts and data inputs into the forecast, I did want to use this opportunity here to just put that into context again, into the broader integrated distribution planning discussion we're having. With that, next slide, please. So in terms of the integrated resource plan, and I'm sure everybody feels familiar in detail here, so it's preaching to the choir a bit. but just as a high level, a couple of numbers here in terms of emission reductions that are being targeted for the state: 45 by 2030, 80% by 2050, and the net zero targets as well. So they are used, as I mentioned in the earlier slide, as an input for the top-down forecast. However, there are certain limitations to how we can use such policy goals. One of the limitations is on here already, is the fact that for DER forecast, and we'll get to this in further slides because the question comes up in multiple points. The way we forecast DER is it cannot exceed system capacity. Right? So as more solar comes online, hosting capacity gets used up, and pending or lack of cost allocation and a planning mechanism for the utility to preemptively or proactively upgrade system infrastructure for lack of hosting capacity, that's where this stalls out. And the DER forecast just hit a limit in terms of what the system can absorb. The other point is, and this is just one item in terms of how the integrated resource plan is set up, that it does not really provide detailed pathways to achieve these objectives. Other states have done that. They've provided detailed pathways looking at certain numbers of heat pumps per year, EVs per year, solar per year, different scenarios to achieve those 2050 objectives. That makes it slightly easier to transform that into a forecast and a top-down forecast than it does for the integrated resource plan. Next slide, please. So going from the state policy topic, the next question went down a little bit in terms of the details. We're now looking at the clean energy programs, and there were a couple of them listed here specifically that we were asked to comment on. Next slide, please. And again, this is just for the context for those people who are not familiar with these programs, which I assume most people on the call are. There were 5 programs specifically listed in the request: the Connecticut Electric Vehicle Charging Program, the Energy Storage Solutions Program, the Residential Energy Solutions Program, the Non-Residential Program, and the Shared Clean Energy Facility Program. So in terms of how these flow into our data collection and our forecast is, of course, we are administrator for these programs, and we track all of the information on charges, on solar sites, etc., that are being funded through these programs, where they're going. That's part of our database that is then used to build out the forecast. Next slide, please. And those programs have evolved over time. And one key item is that they've become successively more ambitious and aggressive in terms of what they're targeting. And especially the shared clean energy facilities and the non-residential programs, they've not only increased the cap size of the maximum project size, both now to 5 megawatts, 5,000 kilowatts, but they've also increased the annual selection volume that can be awarded. Next slide, please. But there is a problem that we see with these programs, which makes it, and I'll get to this a bit later on, hard for us to include them directly in the forecast. And the problem is that if we look at what's awarded and what the future awards are actually, compared to what's going in service, there's a gaping hole between those two values. And what we're seeing, next slide, please, is that these programs have, these programs allow awards for DG sites without checking with the utility on the interconnection cost and the availability of hosting capacity beforehand. And that results in some of these projects, even though they've been awarded, dropping out of the queue. Now, overall, the way we're viewing this is that we have the state policy objectives, which Integrated Resource Plan is one of those, which informs state clean energy programs. Those programs, from our perspective, are designed to achieve the state's goals. And if the state's goals change, those programs will be adjusted, or if the state's programs are not achieved, those programs might be funded better or made more aggressive. On the other side, we have the forecast, and our forecasts, they are already informed by the state policy objectives. So the underlying assumption for our forecasts is that the state will achieve its objectives. From that standpoint, if we're already using the state policy objectives, these programs have very little bearing on what actually happens in the forecast, especially due to some of the downsides we see with the awards being handed out in the programs and then actual projects being realized. But we'll talk a little bit further down in the presentation on how that actually impacts the data. Next slide, please. Yeah, this was what I was just mentioning. These programs allow developers to apply without confirming interconnection costs ahead of time, which results in substantial attrition in these programs. As interconnections are filed, interconnection studies are conducted, costs become apparent, hosting capacity limitations are there, and in lack of a cost allocation or cost sharing mechanism, the developers are essentially stuck with all of those integration costs. The projects do not come to fruition. Next slide, please. And that is a stark fact on our system. We see this in the data, and we've pulled up, I think it's the top 8 of our stations right now that have DER constraints. And what we can see here is that there is none to very little hosting capacity available on those 8 stations. We have substantial amount of DER in the queue on DER online. So overall, system-wide, we've basically got more than 0.5 gigawatts, or 550 megawatts of large solar stuck in the interconnection queue. Again, it goes back to the earlier statements. This is where the issue with the forecasts and these programs and the state objectives comes into play. We have to cut the forecast for the DERs off on the hosting capacity limit, because as we see here, these projects can no longer progress is being built because the stations are out of capacity, and the utility has no mechanism right now to proactively build out that system for hosting capacity. Next slide, please. There's a couple of points from our side on this topic, and I think then that's the last slide on this. This is a common discussion, but we just wanted to reiterate this here. There are certain proposals on the table on how to look at this. One item would be to look at doing group studies, allow larger groups of DER to carry the interconnection cost together, develop a cost allocation mechanism that would allow the utility to recover certain costs and proactively upgrade the system to allow future DG. In such an environment, the DER forecasts could go past available hosting capacity because they wouldn't be capped off at that limit. Next slide, please. This is the last one on the inputs and assumptions. This one was now specifically focused on, well, there's 2 points actually in this question. Number one was the assumptions that we utilize from the generation and transmission systems and how that information is collected and used. And then the second part was more geared to what information from the distribution level from the load and DER forecast is shared back with entities responsible for generation and transmission, which in our case here in New England is the ISO New England. So 2 parts to this. Next slide, please. So the first one's very simple answer. We don't use inputs from the generation and transmission system for our distribution forecasts. What is happening on the transmission and on the generation side on the transmission does not impact the system below the bulk substations, and therefore it does not play a factor in how we do our distribution forecasting. The company does, however, share certain relevant information to the ISO New England for their development of the SELT forecast, which is governed under the ISO confidentiality agreements. So they receive currently installed DER to allow them to build their forecasts. they also receive the ISO report from our end, which includes all of our major bulk station projects. And they receive a station level and a transmission bus level forecast from us. The ISO then uses that data to develop as one of many inputs, because the ISO spans not just our territory or Connecticut, but multiple states and quite a few utilities, uses that to develop then their own forecast. I think that's it for the inputs and assumptions. Moving over to the topic of stakeholder engagement. So before we get started on the slides for the stakeholder engagement, the way we've looked at this, and going to try to answer this here, is twofold. Number one, there's the traditional concept of stakeholder engagement, and I think this is in part what the question was aimed at, is sitting down with stakeholders and having a discussion, potentially where DER might be developed, where load might be developed, where electric vehicles might be developed. And the other side, from our perspective, there's a second portion to the stakeholder engagement. The second side to this is using stakeholder data to develop forecasts. So we're going to look at this from those two perspectives in the following slide, and I'll start off with the stakeholder data. Next slide, please. So from what we're doing here is we collect quite a bit of data, and we'll get to customer-specific data on the load side in the successive slides here. But starting with the DER side, and again, I think this is something everybody here is aware, the company offers not only the hosting capacity maps to developers, but we also have a portal which allows developers to look at projects, siting projects, land availability, and hosting capacity all in conjunction to find ideal areas to develop their project. The utility does have the ability to do anonymized data mining on that information. So we understand where projects are being looked at, where projects are being evaluated, and where developer interest lies. Now, this has the benefit on our side that it is it's not an opinion from stakeholders, but it's their actual development interests where they are looking to spend their money, which from our perspective has a much higher value to the forecast than potential opinions. Next slide, please. And we see that from the data perspective on what's happening on our system very clearly. So on the right-hand side, you have a map that shows all of our 100, I think it's 100 bulk stations in Connecticut. The red ones are currently the ones where we have most of the solar installed. That's installed capacity. The green areas show where most of the interest currently is for solar development. And the orange highlighted areas with respective percentages shows us where most of the interest from customers is on load development. So this might be for large commercial buildings, new developments, or EV fast charging stations. So that is how we utilize stakeholder information to inform our forecasts. Next slide, please. Diving down a little bit into the load side of this, and just to give a bit of context of how this looks. So we have two main load drivers in the state of Connecticut. That's step loads, and I mentioned step loads. That's all of the large new load developments we see. And we have the electric vehicles. So for the step loads, that's a process where our account executives work with all of our national and strategic accounts, so all of our large customers, on what their development plans are. Where do they want to build a new box store? Where do they want to put a new office building in, new lab space, a new factory? And that's information they provide us. And in some cases, they provide us this information way before they go into permitting and siting processes to make sure that they can get that electrical information. So there's a detailed exchange that happens with over, I think we have more than 5,000 strategic and national accounts, where we are in a continuous exchange with them on what their plans and projections are. And we track that in our forecast. Same thing for the electric vehicles. Next slide, please. Oh, this is animated. I apologize. For the electric vehicles, there's two big drivers, right? There's the residential charging And then there's the HVDC fast chargers. And especially for the HVDC fast chargers, this falls again under our information exchange with our strategic and national accounts. So those are all of those accounts that focus on developing charging infrastructure or that want to develop charging infrastructure on existing sites or with new sites they're developing. And we get information again, especially for charging infrastructure in cases way ahead of them siting and permitting, because they do want to make sure that they can pull the power required at the location. And on the other side, this is exchange with government agencies. In Connecticut, we have a very good working relationship with the CTDOT, especially around the NEVI program, where sites are being looked at, and that information also flows back to us on the forecast side. And for the EVs, just to put this in context, right, this was about 53% of the growth forecast. The step loads, we have about 18% of the growth forecast for the state. So in sum, about 71% of the growth forecast are directly related to customer actions and stakeholder engagement on what their plans are. Next slide, please. Moving over to supporting technologies. We can just jump to the next slide. So in terms of the supporting technologies, and again, this is a slide I think we've shown either on the first or second technical session. There are several technologies that come into play. One of those is from Clean Power Research. That's a Power Clerk. Everybody, I think, in the state of Connecticut who has anything to do with DER or renewables is familiar with that tool. It's our interconnection process management tool where developers or individuals can file for an interconnection of a DER within our power system. That tool tracks the information of where all the sites are, what the installed capacity is, and we know what all the incoming DERs are and what the queue looks like. So we, of course, also have SCADA readings on our system that help us to make all of our transfer corrections and back out generation. Next slide, please. Now, the previous slide was for the cleanup of the measured peaks. Now, in the forecasting process, again, the Power Clerk tools come into play because those include all of the existing DG and anything that's in the queue. So that allows us to back out their generation out of the forecast. That's a downward adjustment of the forecast where applicable, so where those programs are. We also have the Grid Twin tool, which we mentioned earlier, where developers can take a look at citing their projects, which informs the DER forecast. We have a lot of vendor data, specifically customer data. We just talked about that for the loads and the step loads that flows directly into the DER forecast, the step loads, and the EV growth information. And then we have some in-house solutions that we've developed that help us manage the step load side and do the EV adoption models. Next slide, please. Level 4, level 4, sorry. Chapter 4, level of granularity. So here, the question was specifically geared to figure out to what detail the forecasts are conducted, circuit level, station level, and what might the limiting factors of such granularity be. I have only one slide for this. Much like our colleagues at UI, we do forecast at a bulk station level. We do that 10 years out with a 90-10 weather normalized forecast. And given that I don't have much to explain what the 90-10 is, I very much appreciate UI doing that before it's my turn. So I don't have to do that on the audio track. But there is a challenge, and the second part of the question highlighted that. And I think this is where the question was going. When forecasting, there are two mutually exclusive objectives. We can aim for a higher granularity, or we can aim for a higher accuracy. As we go for a higher granularity, we reduce the set of potential customers in that forecast. And it gets very hard going to the extreme to forecast a single customer. Like that's almost impossible because personal behavior might change. They might be on vacation that we don't know about. And there's so much that can happen that it is nearly impossible to do an accurate forecast. On the other hand, the more extreme is if you go system-wide. New England ISO, they can forecast with a very good accuracy the entirety of New England on a minute-by-minute basis, day ahead, because it is a very large system with a lot of customers where the uncertainties weigh against each other. So that's the balance we need to strike. And what we use as an input here to strike that balance is the duration time of our projects. Distribution circuits can be developed relatively quickly, weeks, months, maximum a year. Whereas bulk stations have 7, 8, 9, 10 years of project timelines. So as we're looking at this, if we do our 10-year forecast, right, their forecast is specifically designed to allow us to build our bulk stations in time for the need. So that is the level at which we forecast, because it's the maximum granularity we need, allowing us to achieve the highest accuracy possible. The other problem we see if we go for higher accuracy is simply a data sensitivity issue. As we go in and go into smaller and smaller forecast pockets, it's not always possible to obscure personally identifiable information of customers or customer proprietary information. An example given, if a charging developer shares with us their future site development, that's obscure enough at a state level forecast because we don't have to point out to where that is. But if we were to go, for example, for a feeder level, there might be a single site of that developer on that circuit identifying exactly where such a developer is looking to potentially build an HVDC charging infrastructure, which then gives away competitive information of the customer as part of that forecast. So that's the balance we're striking here, and we found historically, and still doing this, that the bulk station level forecast is the most effective way of doing this. Next slide, please. 5, the time horizon. This is going to go really quick. We can go to the next slide because we've shown this slide before and we've just talked about it. We do a 10-year forecast. That is what's used to trigger capital projects. That's what's used to authorize them. And then we have a long-term demand assessment, which looks out all of the way to 2050. That is where we can run multiple scenarios. That's where we can look at different policies, different technology impacts. But that's the 2050 outlook, and that is not used to authorize capital projects. Next slide, please. 6 scenarios. That's a good segue. Let's go to the next slide. So for the 5 and 10-year forecast, there's a single scenario that the company looks at. That is the 90-10 weather normalized forecast at a bulk station level. And we use that as the peak load forecast. Currently, we're a summer peaking system for the summer. On a case-by-case basis, where we are faced with interconnection requests on our system that require an interconnection study, we create a minimum net load for the interconnection studies. Now, that minimum net load will include all the queued DER that are in queue prior to the currently interconnecting. But given at that point, it is essentially a first-come, first-served basis, it does not include any forecasts past that point, because at the point of interconnection, the DER has the right to be only studied under consideration of the system as is, and anything in place up until their point in the queue in the interconnection. So that actually does not include any long-term forecasts, that minimum net load scenario. It is a status of the system on interconnection of the DER. So that's the 2 scenarios. For the purpose of doing system planning and authorizing capital projects, it's the 5 and 10-year forecast that plays into the equation. For the long-term outlook, all the way to 2050, we have a wide array of things we can do. Again, because that's not used to authorize projects in the 5-year capital planning. So how this works, we essentially on the left-hand side, we have a forecasted net station load 90-10 weather normalized for the 10 years. We have existing station headroom. We'll look at all types of solutions, including on wires. We can use flexibility in the system and with resources And then we have a 10-year capacity deficit. This will show up on a station-by-station basis from a load perspective. And as I mentioned earlier, the DER forecast does not go past the hosting capacity, but this is from a load perspective, the capacity deficit. And we develop a plan that looks at that. And then we have the 2050 outlook on the right-hand side. And that goes all the way to the 2050 objectives. And I just put some numbers in here. These are high-level numbers statewide for the non-coincident impact if we were to, example, electrify the entire heavy-duty fleet, the medium-duty and the light-duty vehicle fleets. And then if all of the heating load in Connecticut were to electrify. And to put that into context, right now, our forecast that we filed with the state is about a 5 gigawatt forecast for our Connecticut system. So it's a significant number, right? It goes up. But there is such a high sensitivity to these numbers based on policy measures that might be enacted or charge management or the type of heat pumps that are used. Is it air source? Is it ground source? Are hybrid heating systems retained? That number has a high variance based on the underlying scenario. But that goes back to the original comment for the integrated resource plan. We don't have specific pathways in that integrated resource plan. So what we do is we develop our own scenarios that we can take a look at on how this might play out. In other states, we do have pathways in their state objectives that then are specifically used in this long-term assessment to run out into the future to see where the load on the system might be. Next slide, please. I think this is the last question, and I only have like one more slide. The question was around transparency and how the forecasts are shared. So we publish our forecast system-wide with PURA as part of the statute 16-50R. That's done on an annual basis. The company also publishes station-level forecasts for siting or regulatory approval for specific regions. One example is Connecticut Siting Board, or specifically our dockets with PURA 220605 for the storage projects included station-level forecasts. What we don't do is we don't publish broad-scale entire set of station-level forecasts. Again, this goes back to part of the information that we discussed earlier. A large portion of that forecast load is driven by customer information that we are given directly by customers, and that includes custom proprietary information. So we don't share out that level of information. And I think with that, thank you for your attention. And we're ready for some questions.
Excellent, thank you. We're going to start with questions from authority staff, and then again invite stakeholders to enter the queue, and we will get to stakeholder questions following authority staff questions. Mr. Kramer, please.
Thank you, Chairman Gillette, and Dr. Walker, thank you for the presentation as always, and for revisiting some of the slides that kind of put it together in this specific picture for forecasting. I'm going to start with a few questions on the inputs and assumptions topic. And specifically, for the conversation with UI, we discussed the relationship between the ISO CELT report and their forecasting process. And I know you addressed it briefly, but if you could just elaborate on the extent to which that report is directly informing assumptions around, changes in DERs or other inputs versus the company's sort of own data and using that. Because I think I also heard you say that, as the administrator of various programs, you have that data and are incorporating that into the forecast. So maybe just to put a finer point on my question, is it the case that the company is using its internal data on DERs, these various programs, to integrate directly into its forecast, or is it following that same path that we discussed with UI of filtering up through ISO New England and then back down through the CELT report?
So this is, I think, it's an excellent question, and I didn't go into those details, so it's a good chance to clarify this. And this is where we the process diverges from what was discussed with the UI. So we develop our forecast based on the data we have. And as we've mentioned, we forward all of our DER installed data to the ISO, which the ISO then uses to develop its CELT forecast. But I cannot speculate as to what specifically the ISO's mechanisms are when it gets that data from us to develop the forecast. They get data from a whole array of sources. So since we don't know precisely what's happening in that forecast and what that change of data is as we get it back to the CELT, through the CELT, we don't use the CELT as an input into our distribution system forecasts.
Sorry, just finishing my note
Yeah.
and unmuting. That's helpful to understand. And so then in using the company's data as the administrator of these various programs, and given the relationships with customers and the data you have there, could you elaborate a little bit more on what sorts of, I guess, sensitivities or modifications you might make to sort of project how some of those for UI we talked to them about as sort of out of model adjustments, but I guess my question would be more, how do you sort of calibrate the sensitivities for those DER inputs, given that you have an interconnection queue, but you don't know exactly what's going to come through. So if you could just sort of elaborate on how you account for the projects that are likely to actually come online and therefore make an impact on the system in a given year for the forecast.
That's an excellent question. And if we ever find a really good answer to how to figure out which projects in the queue actually make it through, that would be something. To your point, it's very hard for us to know which projects in the queue make it through and which don't. So a couple of considerations on this. So the first thing is, as I mentioned, we don't forecast DER, specifically solar, past what's available in the hosting capacity. So if you have a station where we showed the list where we're clogged up, that makes that answer really easy, right? That's where it stops. For stations where there is still hosting capacity available, typically the way we play this out is that we do assume, we have to assume that the queue is going to go to fruition, right? From our standpoint, we can't go in and look at the customer data and be like, yeah, 50% of this isn't going to happen because X, Y, Z. The customers have filed interconnections with us. They're paying the fees to be studied. For us, that's an indication that they're being serious about it. So we do consider them.
Understood. So if I understand that response accurately, it's that, where capacity is maxed out, it's a straightforward assumption. And where it's not maxed out, in that case, you would go with the amount that's in the queue or the limit on hosting capacity, whichever is higher, but sort of calibrated for when you think you're going to get there based on the queue for that station. Okay.
That's correct.
Relatedly then, has the company done a study, and this is maybe getting a little out of forecasting, but related based on inputs, but has the company done a study on the extent to which hosting capacity is the limitation versus interconnection costs? You pointed to those two things as being kind of the limiting factors for projects getting through. So do you have a sense of which is more typically the limiting factor for a project dropping out?
I'm not aware that we've done a big study on this, but hosting capacity is the key driver of interconnection cost. In a system that does not have hosting capacity, interconnection costs skyrockets. And from the developer's perspective, hosting capacity is an indication number of where potential system capacity might be available. What will cause them to drop out is not that number being low or high, but is the interconnection cost bill that they will get. So to answer that question, one informs one is a function of the other, and the cost is what kills the project.
Certainly.
Yeah, if I might, Peter, to just chime in a little bit. So I think in one of the interrogatories, there was a question that pertained to this, and we took real pain to delineate between hosting capacity and interconnection studies. The hosting capacity gives an indication of the ability of a DER to interconnect, but it does not take into account all of the performance limitations that would apply in an interconnection study. And so oftentimes developers find that when they apply and when the project is studied, the interconnection cost becomes a prohibitive element. It leads to stagnation in the queue. And as Dr. Walker pointed out, I think in one of his earlier slides, there's about 550 megawatts of DER in this position in primarily 8 substations across Connecticut. And due to the dichotomy of load and DER interconnections in the state, there are areas where we need to upgrade the stations for DER, but there are no load drivers. And so the cost recovery becomes an issue because at this point, we do not use our DER forecast to drive development of substations. We need a mechanism to allow that, and that would be the cost allocation SIP construct as authorized in Massachusetts. Hope that's helpful.
Thank you. Thank you, Mr. Freeman, for that additional context, and thank you also for jogging my recollection of the interrogatory response. I have another question. I think it's also related to inputs and assumptions here, where Dr. Walker, I think if I'm characterizing it correctly, you mentioned that step loads and EVs are the main drivers of load growth in the forecast.
That's correct.
I didn't hear you mention the electrification of heating, and I'm wondering where that lives and how it's accounted for within the forecast process.
That's a good question, and I apologize for not clarifying that in the presentation. So what we've talked about today is our 10-year peak load forecast. And right now, we are summer peaking, and we expect to remain summer peaking up until mid of the decade 2030 to 2040. So if we look at our 10-year forecast right now, summer is the peak driver, not the winter load. And heating will come into the winter load. So we do track the heating installations. We have an understanding, and that was on the last slide, I think, the 8-some gigawatts of what it would take to fully electrify our territory. This is based on air source heat pump assumptions. And again, this is where an abundance of scenarios can be run, but the numbers you saw was just based on 100% air source heat pumps. Well, we keep track of that. As soon as we see in our forecasting that the summer peak is being supplanted by the winter peak, that will change. At that point, heating becomes the biggest driver of the system peak. But numbers here, and this entire discussion was based on the forecast system peak, which is for the foreseeable future still summer peaking.
That makes perfect sense. Thank you for that response. And I'm curious if, in thinking about moving to a world in which the winter peak, supplants the summer, is it the case that, I guess in that case, you would likely, or you might want to track the installations of heat pumps as sort of a separate driver in the same way that you are doing so with EVs, because that would likely be, again, one of the significant contributor to the winter peak.
Yes, and to be clear, anything that's installed through existing programs that we administrate, including heat pumps, where we know what's being funded, we track. The problem specifically with the heat pumps is that there is a large portion that happens outside of any programs or control of the utility. Right? New houses being built or existing retrofits being done. We only see where we are involved through the programs. There is no mandate that anybody switching to a heat pump has to file something with the utility saying, I've just done this, unless they need to upgrade their service panel. So there is the point, there might be a number that we don't see. That's where we use our adoption propensity models that look at personal information for the customers and sorting them into different customer groups and clusters where we assume that they have a certain propensity to adopt heat pumps at a certain time. So we do forecast that out. With AMI development, however, right, if AMI were to be installed, that problem goes away. And AMI would allow us to identify directly who's using a heat pump. It would allow us to see exactly who's doing EV charging and what the usage patterns are. So that would make this forecasting exercise a lot more accurate.
Thank you for that. Okay, I think I have one final question here, which may be a little bit multi-part. But on slide 16, Ms. Lupel, if you could go back to that slide, on the state programs and how they're reflected in the forecast here, I think that I missed something here on sort of the takeaway here, right? On the future and addressing the cost sharing issue. Could you just orient us again to this slide and sort of what how this is being addressed by the company and through other PURA dockets that might sort of illuminate how some of these issues are being resolved?
So I'll let Mr. Freeman talk to, there's an ongoing docket to the cost sharing system, so I'll let him chime in on this. But the purpose of this slide was, right, as it stands today, we have to start with the DER forecast when hosting capacity is reached. The company doesn't have a mechanism to go past that. So DERs are accounted for in the forecast. Where they are present, they reduce the load impact, right? That we've seen this on the other slides with my little nice graphics showing that we use the DERs to reduce load, where load and DERs coincide. And in order to fully roll out the DER forecast on the 10 years and trigger capital projects and approve capital projects based on a DER forecast in regions where there is no load presence or no load driver, as Mr. Freeman has said, and the DER limits are hit and the hosting capacity is exhausted, and we've seen the 8 stations, that would require this. At that point, right, these stations would be authorized for upgrades if we have a cost sharing mechanism to do that.
That's correct, Dr. Walker. And with respect to the cost sharing mechanism specifically, so without getting into the specifics of the straw proposal, I just say that at a high level, we have been advocating along with stakeholders for a mechanism in Connecticut that allows us to proactively build substations in areas where there's a high demand for DER, where there is a proven availability of land, and where there are historical issues with regard to cost causation and queue stagnation that have kind of curtailed the amount of DER at particular stations. We know that such a mechanism has been approved in Massachusetts, and we know that the way it was approved guaranteed cost recovery for the utility in taking this risk to build these substations. We have written comments that we are developing for the straw proposal, but suffice it to say, it does not align with what was approved in Massachusetts, and we have concerns about that mechanism as it's proposed in Connecticut.
Thank you both for coming back to this. I wanted to make sure that I don't want to go as you're suggesting, Mr. Freeman, not into all the details of that, but I wanted to make sure that we connected the dots there, and that sort of key takeaway of what would be needed to expand capacity was addressed here. So thank you.
Thank you for the question.
Of course, Chairman Gillette, that's it from me.
Very good. Then we are going to turn to our stakeholder questions, and I see Mr. Walmsley again, please.
Thank you very much. Yeah, Alex Walmsley with RMI, working with the Office of Consumer Counsel. Now, my question is about granularity, and please correct me if I've misunderstood, but I think we heard from UI a discussion about trying to make forecasts more granular and looking at bottom-up modeling and trying to kind of dig down into the lower voltage levels to better understand what's happening at that kind of granularity. And I think we heard something quite different from Eversource, which was saying that the forecasts at the bulk substation level are sufficient, and that allows you to make the right kind of decisions. Now, I'm not looking for Eversource to speak on behalf of UI at all. I'm more just curious as to if you could expand on why it is, if I've understood this correctly, that you're not looking to have more granular forecasts or more bottom-up forecasts coming through.
Thank you for that question. And I'm not going to go and comment on the methodology UI uses, not in detail familiar enough with that to do that. But from our perspective, and I don't have that slide here, but I think we've shown this in one of the previous technical presentations, is we have different project time horizons. Feeder circuit upgrades, pull mount upgrades go pretty quickly, and they have leadways of weeks, month, maybe a year. So for an asset that I can replace in month to a year, I don't have a need for a 10-year forecast. And a 1-year outlook is fully sufficient to be able to exchange that asset. For a substation, where I need to go through siting, permitting, extensive community engagements, and this entire process takes multiple years. Like, we have projects in other states where we're past the 10-year mark and the station isn't built yet. We need that long-term forecast. In an ideal world, if I can snap my finger and make a station appear, nobody would be doing forecasting, because forecasting has inherently the risk of being wrong, and there's no such thing as a perfect forecast. So it's a method for us to compensate for the duration of infrastructure build out, because I need to have the infrastructure ready when the need is there. So if I look at it from this perspective, I have a substation, 8 to 10 years, so I need to forecast 10 years. A circuit, month to a year. If I do a 10-year forecast, that's irrelevant to that circuit, because that circuit might have changed, might have already been upgraded in that time. We might have reconfigured it. So that's one piece of doing it versus not doing it. The other aspect is just from a statistics perspective. And I think like the best example is the rolling the dice kind of example. If I roll the dice 10,000 times, I can tell you that with 1/6 probability, every number comes up, and I'm going to be very accurate on doing that because I roll 10,000 dice. If I do that with 2 dice, my predictions are going to be really bad. So as I shrink, the same thing goes for the number of customers. If I have to figure out which customer is going to adopt an electric vehicle, if I do that across 10,000 customers and I say 600 of them are going to adopt an electric vehicle, that number is more likely to be correct rather than looking at 6 customers and saying 2 are going to adopt an electric vehicle. I just have a much higher uncertainty the smaller I make my set of variables. And so unless I am forced to take a look at that granular aspect, which has the higher uncertainty in it, it doesn't make sense for us to do it. And since, as I mentioned earlier, the construction timelines of our system infrastructure doesn't warrant us to have a 10-year forecast at a circuit level, because again, we can do that very quickly, we don't create it. So that's the logic in terms of why this isn't done.
Thank you for the clarification. I assume with the statistics example, it's probably a non-linear rate at which a forecast becomes less useful. I'd also, would it be right to characterize that your build out of things which are smaller than substations is essentially more reactive? So you can react and respond to what changes and just build something without needing a forecast. Is that roughly what you're saying?
And that's essentially the point, right? As I mentioned, if you could wave infrastructure into existence, I wouldn't have a job, because then the utility would do exactly only what's needed at the time it is needed, and you wouldn't have to do that preemptive planning for the infrastructure. Now, we live in a world where that's obviously not possible. So yeah, we do the planning to the level that we needed to get the infrastructure in place.
Okay, and then that, I assume, will have some impacts with the REO1 docket, which is specifically about, for instance, how much funding is within a multi-year rate plan if you are reacting and responding in shorter time periods. How do you see that fitting in with a multi-year rate plan type program?
I'll defer that one to my colleague, Mr. Freeman.
No, so absolutely, there are, as I indicated before. Well, so two things. Just to step back a little bit, and Dr. Walker is completely correct. Forecasting in and of itself is not the goal. It's not, it's not a noble activity in a vacuum. It's all about how do we use the forecast, right? With all due respect to Dr. Walker and his activities, right? It's all about how does the forecast fit into distribution planning? And to go back and talk about the feeder, I'll get to your question. With the feeders, I just want to emphasize what he said. Every day, every single day, our feeder configuration changes. We have ties, extensive ties between distribution feeders, and for reliability reasons, during faulted conditions, we reconfigure our feeder. So forecasting down to the feeder level doesn't make sense from that perspective because it's never static. But also, even more to the point, as Dr. Walker said, we can build a feeder quickly. We are not completely in a reactive mode. We do plan ahead. We do look ahead at what the loads are on the feeder, what we anticipate in terms of demand, and we do proactively build feeders, but the lead time is nowhere near the substations. And so feeding into the rates and the recovery mechanism, absolutely. We see the need to build substations and to start that construction for load, for DER, but we also need to have guaranteed recovery on these. Sometimes they are not used or useful for years. And then how we do that, I think, becomes a very valuable discussion in REO1, how we treat distribution projects at a feeder level that we can build very quickly. I think those aren't an issue. The substation projects that take years to go into construction, the utility must have a way of being able to keep itself whole and ratepayers hold with mechanisms. So that's what I'd say. This is a ongoing discussion in REO1, but I won't get too deeply into it.
Do you have time for just a quick comment, a quick question? I am now a little confused. On the one hand, you're saying you're not forecasting past the bulk substation, but you're also saying you do proactively plan for feeder upgrades, but not by a forecast. So if that's not a forecast, how do you proactively plan for things which are smaller than substation upgrades?
So well, it depends on how you look at proactive. So we do understand that at the feeder level, the imminent drivers are right now it's load, right? And right now it's to be precise, it's step loads. And so once we have some knowledge, some certainty about the development of a step load, then the feeder construction begins. So you can look at that as reactive. We are also looking at the impact of electrification and driving that down to the feeder level. Okay. Now, that doesn't lead to imminent construction, but that gives us an idea of which areas of our system we expect to see electric vehicle charging stations, impact of heat pumps, and begin to position our construction so that we're meeting imminent needs, but we're also taking into account what the long-term drivers are. And so the ability to reactively plan for imminent load and to position ourselves long-term proactively for future needs is a balance that we're always trying to maintain so that we don't tie ourselves into a configuration or construction mode that does not lead to expansion for long-term demand when we look at electrification. I hope does that clarify that? I know I used a lot of words, but I'm hoping, yeah.
It was helpful to hear you discuss it back. Thank you.
Okay, great. And it's the same thing on the substation level, but with a much longer time frame. We plan our substations for imminent need, but we may, for example, when we plan a three bank substation, we may make provision for fourth bank. We don't put it in yet, but we may leave room for fourth bank because we know in 15, 20 years, there will be electrification demand that would enable us to expand that substation, and we don't want to lock ourselves into a design that is not expandable. So maybe that example is a little bit more helpful.
Thank you.
Thank you. Are there other stakeholders with questions for the Eversource team? All right, seeing none, I want to thank Mr. Freeman and Dr. Walker for their presentation, for answering our questions.
Thank you.
Thank you for having us.
Great. So the remaining items on our agenda include the time for any open discussion items, and then I will briefly recap next steps for this docket. So if there are stakeholders who wanted to provide a comment and haven't had an opportunity to do so today, we just wanted to provide this space. And I'll pause here if anyone wants to be heard today. It'd be helpful if you found the raise hand function under the reactions tab at the bottom of the screen, but also welcome to take yourself off mute, and that should flag my attention. All right, if not, then that brings us to the end of today's agenda. The calendar for this docket is up to date. It is available in the docket. We have some ongoing discovery that we'll be engaging in. And the next time that we will see folks back together to discuss items in this docket is not too far away. We have a fourth technical meeting scheduled for February 6th, beginning at 1 p.m. So we will see folks back here and keep your eyes on the docket for the notice of that technical meeting, and the topics and requests for presentation will be included in that notice. With that, I want to thank both teams for their presentations today, and for our stakeholders for their questions and for attending. And with that, we're